speaker. So let's move on to our second speaker, Professor Subarao Kampagati from Arizona State University.
Okay. Thank you for inviting me for this Samsung AI Forum. I'll be talking about how LLMs reason. It's sort of well connected to the whole agentic systems aspect that we'll be seeing in a minute. For those of you who want to follow along, the slides have actually been posted. So that's a bit.ly link that might come up again. So you can look up there. Okay, so let me start by mentioning that I was here in 2020 for Samsung AI Forum. That was the first of the pandemic ones, unfortunately, because of which I had to do it by Zoom. After that, I've actually done a bunch of things in Korea again by Zoom on various TV shows and so on. So I'm kind of slightly disappointed that I'm again doing it by Zoom. Hopefully, one of these days I'll actually come to Seoul. But thank you again for inviting me. I am work in automated planning. My career has been in automated planning and decision making. So the important thing for an agent is what do I do next, given the environment, the kinds of actions it has, the kind of sensors it has. And these can be software agents, they can be physical agents, and so on. And most of my life I have spent on actually figuring out how to do planning in under different kinds of circumstances. So that's sort of well connected to essentially agentic systems, because as we'll see in a minute, as basically the agents really have to plan to achieve specific tasks in the real world. And so basically, really, I'm going to be talking more about a particular form of reasoning, which is planning, and how do LLMs plan. And from that, you'll get a lot of interest, connections to general reasoning aspects too. Okay, so in general, I want to kind of make the distinction between being able to act, which is like calling tools, etc., and being able to plan, which is making sure that the calls that you're making are going to be connected towards some high reward for you. If you don't know what you're doing, just by doing actions, you can get into lots of trouble. For a minute, think about leaving a gun lying around in a home with a toddler. The toddler would know how to use the gun, but doesn't quite know what is the right ways or wrong ways mostly to use them. So in general, it's clear that LLMs can essentially do tool calls. One of the interesting questions that we also need to know whether they want to be agentic systems is to what extent can they do planning for themselves. You can actually do orchestration from outside, that will work fine. But the question is, can LLMs also do orchestration themselves, and under what conditions can they do it? And so to do that, actually, we started by basically looking at this, a couple of years back. And then, the general idea there was that people are assuming that LLMs can already do planning. Lots and lots of papers were written before 22 itself. And so the question, of course, is whether that does make any sense, especially these are the standard LLMs. These are the ones that we're talking about where you have autoregressive simple LLMs. These are not even the reasoning models that we'll be talking mostly about today. And the problem with LLMs that some of you have probably realized is they have a huge memory effect. Their intelligence is kind of jagged, so they can do pretty amazing things, such as winning international math Olympiads, but just fail flat on very simple kinds of reasoning. People keep showing this all the time. This is one of the recent ones where somebody asked ChatGPT-5, Amazon sent me a left shoe instead of a right shoe, and a right shoe instead of a left shoe. What do I do? And ChatGPT gives a multi-step plan trying to send all the shoes back, even though it's obviously clear that the shoes are fine, right? So in general, the fact that they can do well in something doesn't necessarily mean that they can do well in anything else. And this is a big issue because of the memory effect of LLMs. So when you think about autoregressive LLMs, compared to humans, essentially who have both system 1 and system 2 for deliberative reasoning, planning and reasoning tend to be deliberative, LLMs really should be seen as like a huge external system 1 for humanity as a whole. And so the question then is, why would you expect them to do planning correctly? So we actually started checking this like a couple of years back, and there's a bunch of papers on this. So for example, in NewRips, we basically have this series of 3 papers showing that if you think of planning as actions with actual interactions, such as something extremely simple, such as stacking blocks on top of each other, or doing logistics, it turns out that actually their planning performance is pretty abysmal. And it becomes even worse if you change the names, so obfuscate the domain. We have shown this, and of course, we also shown that other kind of ideas as a chain of thought and React don't necessarily help as much. In particular, chain of thought helps improve performance for the examples that you have given, but as the length of the examples increases, they fall down. So something as simple as last letter concatenation, it starts high enough after you give a chain of thought prompt, but as the number of words increase, it just starts falling apart. So there were papers on that, and NewRips 24, NewRips as well as KMLR on those things. Should not be surprising that LLMs can't take advice because in a guaranteed way, because after all, as John McCarthy said, one of the goals of AI itself is to be able to take advice and follow it correctly. And so it's a pretty hard problem. So it should not be surprising that auto-regressive LLMs can't do this. So the question, of course, is then why are people actually at that point of time saying that they could do planning? And it turns out planning has like 2 really different pieces. One is knowing what possible actions are there and whether you can even make up actions if you can't think of, if you haven't been given those actions. And secondly, making sure that the actions can be sequenced in such a way that they don't run into problems. That means there are no interactions. And if you have played any blocks world kind of scenarios, you will know that the order in which you do the actions winds up making sense. If you want to put A on top of B on top of C, first you have to put B on top of C and then put A on top, otherwise it will not work. And in general, interactions is what actually makes that part complicated. LLMs are actually very good at the planning knowledge part, but they're very bad at the interaction resolution part. And we can show this by taking something as simple as blocks world and removing all the preconditions and the delete list so that the actions don't get into each other's ways. And if you do that, actually the performance of LLM, accuracy performance, improves quite significantly. Still not 100%, but it improves significantly. In general, so autoregressive LLMs will do fine if for planning if your domain doesn't have action interactions, and action interactions are connected to what has been called ergodicity of the domain, ergodicity of the world. An ergodic world is one where essentially it's a forgiving world. You can go from any state to any state with non-zero probability. So ergodic worlds don't have death, they don't have accidents, and so in those kinds of scenarios where you can't overwrite files, etc., LLMs actually are fine because the planning itself is kind of less critical. Knowing what actions are relevant are probably more important. Now, that is about autoregressive planning LLMs, and we have written a bunch of papers on that. But as of last year, approximately just about last year around this time, September 12th, 13th, actually, if you might remember, some of you might remember, the strawberry model, the O1, was released by OpenAI. And the difference between the standard LLMs, which are autoregressive, and the reasoning models is they have these 2 ideas that I'll talk about in a minute: test time scaling and post-training. And then I basically want you to understand why they help and how they don't help necessarily. That's what I'm going to do. So we, in fact, last year, we spent a bunch of time writing, basically digging into this and writing a bunch of papers, some of which are shown there. But I basically want to walk you through, a perspective on how do you go from what was originally a system 1 for humanity, which is autoregressive LLM, so that it will actually also have sort of system 2 style behavior, something like reasoning. So that's the kind of thing that we want to understand. How would you go about it? One simplest idea to start from is that think of LLMs as idea generators. They can generate ideas about everything, including actions, including plans. They might give you a suggestion of this could be a plan, etc. And so the question then is, if you use LLMs as the idea generators, then if you have some verifier in the loop that checks whether the idea is correct, then you have a verify, generate, test loop. And the generate test loop is essentially how you start getting guarantees about reasoning from LLMs. And this has basically been called test time scaling. I'll make in a minute. But in general, AI systems So basically, having the ability to generate ideas from LLMs can be used along with a verifier. So there is a bunch of ideas for test time scaling, including just let's generate a huge number of suggestions for plans and then maybe take the one that has the majority. It's been suggested more times. But a better idea that I like, which especially because it's connected to our work, is what I call LLM-Modulo, where you use a large language model as a generator and you have a bank of critiques or verifiers that critique the plan from various different angles. And if there is any problem, they will give a prompt back. It's called back prompting instead of backtracking. And this back prompting can be used to come up with a next suggestion from LLM. And then this generate test, if it ever ends, in the sense that if in fact critics are happy or the majority of critics are happy, then you can send the plan out and you actually will have guarantees that the plan is correct in this case. So one of the questions, of course, is where are these critiques coming from? One obvious idea would be to try and say, let's just use LLM itself as a critique. I'll show you in a minute that verification is, while oftentimes cheaper than generation computationally, LLMs are not necessarily any better at verification than they are at generation. We have a iClear paper that I'll talk about in a minute. But in general, there are actually verifiers that might be available for your domain. And so you could use them. You can also learn verifiers. And when you're learning verifiers, you can either learn them as either LLMs, fine-tuned LLMs, or some sort of learned neural networks or something, or you can also actually have LLMs to generate code for the verifier and have the code checked in an LLM-Modulo loop. That's a synthesized verifier, so that's also possible. And then these kind of verifiers can essentially be about correctness. Mostly that's what we'll care about in terms of agentic systems, safety aspects. And they can also be about style. And for the style, actually, LLMs are much better because there are no actual classical techniques. But for correctness, you tend to have to either have learned verifiers or the verifiers from outside. If you use LLMs directly out of the box, you can actually worsen performance. I'll say in a minute. So LLM-Modulo, we have shown in ICML last year that it actually improves performance like significantly from the base LLM. And the more number of iterations you allow between generate test, the higher the accuracy is. And furthermore, when actually a plan comes out, it's guaranteed to be, it has passed the critiques. So this is how actually human experts looking, NASA, human experts looking over multiple mission plan being generated, will all of them say, am I happy or not happy? And then if they stop critiquing, if they're fine with it, then you will say the plan is correct. And so that's the kind of thing that you can do with LLM-Modulo, and it actually provides some guarantees about the plan correctness. And another important thing to remember is we're not just giving it to some classical solver outside. We are using verifiers. They're actually composable. And in general, solvers are verifiers plus search. And we are letting LLM actually do the generation of the ideas. Okay, and as I mentioned, actually, to the extent critiques have good properties, those transfer to the solutions being sent out, and this is how you can get safety considerations met. As I mentioned, if you actually wind up insist on using LLMs to do self-critiquing, sometimes actually LLMs might very well walk over a correct solution only to stop with a wrong solution, because they might actually have both false negatives and false positives. And in fact, in the iClear paper, we show that in several cases, actually, LLMs being self-critiquing themselves worsen actually the performance than LLM just guessing one and then calling it a day. So that's the thing to keep in mind in terms of just using them directly as verifiers. But to use them as style critiques, it actually makes a lot of sense. There's a paper in COMB last year which shows that a vision language model in this case can actually critique a behavior, all of which actually reach the goal, but some of them may be better than others from the implicit human constraints. So for example, in the lowest one, you don't want a robot to give you a pair of scissors with the pointy end towards you. So that's a bad thing, and that's something that VLMs are actually able to capture. And it's much harder to get classical verifiers of that sort, classical style verifiers of that sort. Okay, so that's about test time scaling. And in fact, it guarantees that there is no mystery there anymore. You're just using LLM as a generator, and you're using a verifier to see if any of the generated ones are actually good. And the power comes because LLMs are actually pretty good generators for many, many domains. They don't give up. They actually generate things that are kind of possibly reasonable, and then the verifier makes sure that they're actually correct. But as in fact, one of the problems, of course, in the test time scaling is this is all happening in the user facing time. And so you don't want to wait after you hit return, you want answers. So the question is, how do you make sure that this test time scaling, which does work, actually is somehow compiled back into the base model? Marvin Minsky, another of the founders of AI, basically said intelligence is integrating test part of the generate test into the generate part. And that's what we do when you do post-training. One example in this case, for example, is you can essentially take this LLM-Modulo idea that I had and basically get a large number of problems and then try to solve them. And you have verifiers, they check whether the solution is correct or not. And then you have a whole bunch of synthetic data. Now you can fine tune the LLM back. That idea is basically the start of post-training with the synthetic data, except the real post-training that is actually become more popular does a couple of extra things. One is you not only, you basically not only do fine tuning with SFT, sometimes you do fine tuning with RL, reinforcement learning. I'll tell you in a minute how that changes things. And the other thing is essentially that you also have intermediate tokens rather than just give problem and answer and fine tune. You say problem, a bunch of intermediate tokens, and the answer. And these intermediate tokens it's not well explained as to where they come from. It could be humans trying to give step-by-step instructions. It could be like an outside solver essentially giving its data structure manipulations as the trace time, as we'll show in a minute. And these intermediate tokens with the synthetic data, if you then either SFT or RL, that basically improves the accuracy of the base model high enough that you start having better performance. No guarantees, but better performance. It becomes a better generator. In terms of the RL part, all that actually happens is you have the base model generate K trajectories, K intermediate tokens followed by a guess on the solution, and you have an actual verifier. This is why it's called RLVR, RL with verified rewards. So the verifier actually evaluates the trajectories that end in the correct solutions and reward them. And then you use the policy gradient methods to push the LLM parameters towards the good trajectories. And if you do this long enough with a large amount of synthetic data, then you will start having base models that have higher accuracy, but still no guarantees. There are all sorts of issues as to whether or not RL is doing anything much more than SFT that I'll get to hopefully, but that's basically where RL is. So when I gave a talk back in last August in ACL as a keynote about whether LLMs can reason and plan, by that time, remember, there's only autoregressive LLMs. Right after that, in September, when this Owen model came along, Noam Brown basically tagged me and said, look, Rob said certain kinds of planning problems can be solved, but Owen does solve it. So in fact, we did do a systematic evaluation. There was one paper right in that month, and then there was a longer version of that in TMLR. And basically the answer is yes, reasoning models are better. As I said, they're better generators than the autoregressive LLMs, direct autoregressive LLMs. In essence, they are training themselves with significant amount of extra synthetic data with these, intermediate tokens about which we'll talk about in a minute. And this accuracy, they do start with a high enough accuracy. Like if you look at these curves, in terms of the plan length, and the lower plan lengths, the O1 performance is quite high. The very top is, of course, the actual Oracle performance, the 100% accuracy. You see that they're much higher to begin with, but then as the length of the plan increases, they keep falling down. So they degrade in performance as the expected length of plan increases. And they're also particularly worse in the paper we show that on things like unsolvable instances. The reason why this happens is not that hard to understand if you get the perspective that what is happening when you are doing the RL trace, the way that I mentioned, is that essentially the base model has a top K accuracy on a certain set of problems, and the RL or the SFT makes the top K accuracy become closer to higher top 1 accuracy on that bunch of problems. In doing so, it improves its top K accuracy on the next larger set of problems, larger length problems. And this has to be done incrementally. So basically what you can think of is that the reasoning models are slowly compiling the verifier signal into the generator. It's not a bad thing if you're using the LLMs as your go-to thing and somebody else already spent all the time doing this post-training, but this is really what is happening. It's incremental compilation of verifier signal into the LLM, the base LLM. And one of the other things to understand here is in machine learning, essentially people are always talking about in versus out of distribution, and LLMs actually try to shortcut the out of distribution problem by saying put everything in the training data so that there's really nothing left outside. This almost works except in reasoning problems, because there are essentially, if you take something as simple as last data concatenation, there are infinite number of last data concatenation problems. There are infinite number of block solved problems with increasing lengths and so on. And if you can pick up the algorithm, that's just a simple algorithm. But what LLMs are doing is essentially incrementally compiling longer and longer plans, longer and longer solutions back into the base model. DeepSeek R1 is actually competitive with O1. We show that too. And more interestingly, I think 2 months or 3 months back just before summer, folks in Apple redid these experiments, except with even more, like not just the O1 and DeepSeek R1, but also Claude and various other things. And they basically showed the same results that we have shown, which is that as the length of the plan increases, the performance plummets. You can see this as that's okay. If I don't really like particularly long plans, then I still have this particular model will be fine enough for me. Interestingly, so there was actually much more of a surprise at this for some reason. It shouldn't be surprising if you heard what I'm saying, which I've basically been talking about before too. But then, it turned out that Apple paper kind of got some, people be surprised at the results. And then the New York Times article, which does actually point out that we did this earlier work on that. Okay, one other point is, I said that the performance improves, the generator's performance improves, but no guarantees still. So what if instead of using LLM in the LLM-Modulo, I used LRM? That means I use O1 or Claude or something, and then put it in a verifier loop to actually generate verify loop, to make sure actually that if you in fact safety matters to you, that's pretty much the only way you can get safety critical plans. And so this will show that this sort of a large reasoning model actually, and one of the interesting things is this large reasoning model now is not only doing post training, but is again doing test time scaling actually, because you're doing, the verifiers are checking whether the solution you produce is correct or not. And if you combine that with these verifiers, you can get both higher accuracy and actually guarantees that in fact what you're saying is correct is definitely correct. Okay, so the TLDR on this basically is that if you're trying to deploy LLMs in agentic systems, make sure that the scenario you're working with is ergodic. Many software tasks, basically tend to have this property, especially if you are not overwriting databases, and so that you can walk the things back if the plan goes wrong. And then, so mostly what you're celebrating is that they can make complex tool calls, and that's a reasonable thing to celebrate. If the scenario is non-ergodic, consider test time scaling and verification techniques, either LLM-Modulo or LRM-Modulo, and then invest time on providing and or learning good verifiers. The good verifiers are important both for the post-training, which is basically RLVR, which is basically LLM-Modulo being done during the training time, and also for the outside, because you want to improve, guarantees about, correctness of the solutions that you're providing. Okay, so that sort of is the bigger points I was going to get at. But now I want to talk a few things about some bleeding edge stuff that we're doing about understanding some of the issues around LRMs. One of the important ones tends to be the intermediate tokens. The second is RL formulation. Let me see if I can get you through intermediate tokens idea. So the intermediate tokens have been often thought of as the thoughts. The model gives some thoughts before it gives the answer. And there's this idea that people can read these thoughts and see if the model is actually correct or not. And so it's very important to distinguish between two different roles of intermediate tokens. One is the intermediate tokens. Everybody agrees that the intermediate tokens are, training with intermediate tokens is helping the LLM's accuracy. One question is whether you can interpret the intermediate tokens mechanistically in terms of why the LLM is doing better because of these particular intermediate tokens. The second is, can the users understand these mumblings and somehow do something constructive with them? And the first is fine. The second turns out to be a huge problem. I want to convince you of that. So in particular, why do intermediate tokens seem to improve accuracy? My perspective is essentially that it turns out a right prompt augmentation can always increase the probability of completion happening to include the correct solution. And these prompt augmentations don't actually even have to be understandable to you. It just has to be a series of tokens that LLM makes sense of. And if you remember, LLMs essentially are thinking of all words as essentially points in this embedding space. So in fact, the prompt augmentation can even be from the continuous latent space. And it can actually, there is work showing by others showing that that sort of a thing can also improve performance of the LLMs, accuracy performance. And you can clearly see that the continuous latent space tokens won't make any sense to the humans, clearly. Okay, but people think that since the intermediate tokens tend to be in English, some sort of a pseudo-English. In fact, DeepSeek R1 first had DeepSeek R0, which was just, essentially doing the post-training with RL. And then they found that it was combining English and Chinese. Then they overloaded it to only produce pseudo-English by doing additional supervised fine-tuning so that it will only do actual English sort of pieces stuff. And then they basically said that people can now understand these intermediate tokens and they can trust the results well. But that turns out to be a very bad point, because essentially these tokens that they generate tend to be a humongous amount of pseudo mumblings, which actually nobody really tries to, can make sense of. So for example, R1, DeepSeek R1, solving a simple 4 block, in this case, mystery blocks for problem, starts saying the following things as its intermediate tokens are quote unquote thoughts. This is the first page. That's the second page, third page, fourth page, fifth page. So 5 pages of stuff that if you read, it's in English, but it doesn't actually go anywhere. It's garden path mumblings. And what people do is they look at pieces and say, hey, it seems to make sense. It says here, aha, here it says, let me verify. So it must be actually doing that stuff. So this sort of should remind you of, if you know, a Rorschach test, where essentially ink blot tests where people start seeing patterns that they are evolved to see rather than by design, the pattern actually being present. So, but the question, of course, is how do you show that they don't actually have meaning? It turns out that for the DeepSeek R1, it becomes very hard because there's a whole bunch of English. I don't know how to simulate that. So we did this work, interesting work, where we train an A-star search algorithm on a bunch of, we train an empty transformer with a bunch of mazes being solved by an A-star search algorithm. And these mazes are generated from very different distributions. And then you essentially try to see if, in fact, you can try to see if, in fact, this particular trained model, when it produces the tokens, it will also produce the A-star search like traces, such as creating open list, closed list nodes. And A-star search can simulate those, and then you can see if they're making any sense. We find at first that there's actually no direct correlation between the validity of the trace and correctness of the solution. And that made us think, what if you actually trained the model with swap traces? That means you give the problem somebody else's trace and the correct solution for this problem. So every problem has wrong trace. And if you train like this, you find that this swap trace model still actually has pretty high accuracy. In fact, it has even better out of distribution accuracy. And yet, of course, its plan trace validity is 0 most of the time, right? That sort of tells you that the validity has no connection to the accuracy directly. And then we also show that RL improves accuracy, but does not necessarily have to improve trace validity, especially in the case of these, models such as the swap model. And then the last thing that I would have time to say here before I just stop is reasoning length. So the length of tokens is being connected to, maybe it is connected to the problem complexity. It turns out we actually checked this, and by actually taking that transformer trained on real hard mazes and asking it to solve trivial mazes where S and G are both in the free space. And you will see that basically it dies on these problems, and the amount of tokens it generates has nothing to do with the complexity of the problem. In the plots below, the x-axis shows you the actual complexity of the problem in terms of how many steps, how many operations A star search has to do, and the y-axis shows how many intermediate tokens are generated, and you see there's basically a disconnect there. So that sort of makes you think that, and we also saw this in the Q&A tasks, and we actually showed that the ones that improve accuracy are not actually making sense to humans if you do human subject studies, and the ones that make sense to human subjects don't necessarily improve accuracy at the same level. There is a bunch of things about RL that I won't have time, unfortunately. It turns out that it's a degenerate MDP formulation, because of which it's close to essentially incremental supervised fine-tuning. And then the increase, people have tried to assume that RL increasing the token length, RL trained models giving longer and longer tokens is an indication that it is actually improving its reasoning. And we show that it is actually because for wrong problems, you will always have much longer traces than the right problems. So that's basically RL improving thing. And so the perils of this is, if you are saying they have meaning and they don't have meaning, then people can actually start trusting solutions that are actually wrong, and that could be a problem. And so there's actually some coverage on this thing. And then I said, if you're deploying LLMs and LRMs in agentic systems, you should be careful about this. They're very useful in some ways, but they're also currently, yet they have their interesting, the autoregressive models don't work at all in non-encoded domains, and the reasoning models basically don't necessarily generalize too far, but they do have these issues about intermediate tokens and so on. So I will stop here. Thank you for your time.
Thank you, Rao. So we are going to Q&A session. We'll invite both Rao and Joy on the same session.
Excellent.
Okay, so I guess you guys talk related. So Joy was talking about agentic system starting from the LLM and how to build upon that, while Rao is going into the LLM more deeply. So there are some common things between your talks. One thing that I noticed is in advisor model that Joy was mentioning, in a sense, it's kind of prompt augmentation that Rao was saying, right? So, but then this is somewhat a controversial question, that Rao is saying that intermediate tokens doesn't have to be interpretable and it doesn't have to be the best prompt, right? So how does it actually help, Joy, when you do this advisor model? What is exactly advisor model is doing to the black box model? And
yeah, it's a good question. So what we're doing with the advisor model right now is we're trying to provide more context to the problem. Often it might be learned information about the user that I want to put into the black box model, but I can't because it's fixed. I think Professor Rao's comments are more, and I actually agree with them, that the context generated through reasoning isn't for us. It's tokens that guide the model to success. And as we do RL on these models, they often become gibberish. And people get upset about that, and they shouldn't. The gibberish is there for the model to get to its answer. Sort of like, in your head, there's likely gibberish that gets to an answer as well. We don't need to see that. That is for the model's purposes. But the instructions that we give to the model are how we steer it. And the idea that the model is pre-trained and post-trained, the black box model, to take some given set of instructions and then proceed is important. Again, the kind of the think tokens are often, as we find in the latest models, hidden in blocks that delineate that piece of the context as the kind of the property of the model to generate the tokens it needs to generate the answer. But again, those are distinct from the instructions we give.
So Rao, I have a question here then. Are we doing post-training wrong? So you are saying that the current things that are not really doing the best of all, right?
So yeah, I think research is such that we are always doing something wrong that we will improve a few years from now. And people in academia that you used to be at one point of time, and Joey and I are still, our idea is to try and see what is still missing here. I actually missed one slide. I didn't want anybody to think that this is supposed to be anything negative about LLMs. Skepticism is a good inductive bias for good science. And you just need to understand that the current RL system that basically DeepSeek R1, one of the other things you have to understand is right now we only know one frontier model, how it does actually RL. That's DeepSeek R1. Nobody else writes papers anymore, which is basically you're trying to read the blogs and try to see what they might be doing. And interestingly, the one DeepSeek R1, I have humongous respect for them because they actually publish something. But the point is that actually shows also that the way they're doing it is they make the baseline trajectories, generate K trajectories and hope that one of them is right. And if none of them is right, there's nothing going on with RL. And that started basically an entire cottage industry of people trying to generate more trajectories, kind of sorting them in terms of the length and taking the few top ones. But if you remember what I said, the correct ones tend to have shorter trajectories, so the long ones tend to be wrong. And so when you sorted it, you are essentially picking more and more correct ones. And then sampling just the top doesn't mean that you spent a lot more time trying to solve synthetic data problem. I've heard 4 times removed that systems, some places like Gemini, etc., are actually doing more more like LLM-Modulo sort of thing, where they basically might be doing MCT style post-training in the training phase. So all I'm saying is, if the stuff that you write, I can critique and then point out what is wrong with it, and then that actually makes you think about what else needs to be done. So as to are we doing post-training wrong, we started doing post-training right now, and we should understand what is right and wrong about it. And I enjoyed Joey's talk. It's like there are 2 very different things you have to do. One is, given where you are, how do you go forward? And then also make sure that did you get this to the right place, or should you be getting to a different place? And in some sense, that's the complementarity of these 2 things. And we will have better post-trained techniques. We will have less of a craze about intermediate tokens having semantics, because that's just wrong. And in fact, by the way, that actually OpenAI and Gemini most of the time don't show you the think tokens. They show something, and people think that is the think token. That's actually potentially post-facto computed explanation of the solution. So if you see the open source models that OpenAI has sent out, it has 3 pieces. One is think tokens, one is the summary tokens, and one is the solution tokens. And the summary tokens essentially is a part of the solution in some sense, and you're trying to communicate with humans with that. So if you want to communicate, plan for that. If on the other hand you want to think, your thinking doesn't have to make sense to me. Essentially, your thinking only has to make sense to you in coming up with the correct answer.
Joey, you have done a lot of post-training. So what's your insight here?
Yeah, so I was going to say post-training is hard. One thing I think people don't appreciate is the base ingredients matter a lot. If you're doing something like reinforcement learning, it's pretty critical to have some of the basic behaviors present in the model. It is possible, this learning from zero to thing, but that just takes a lot of rollouts, in some sense luck, to get to good observations. Things like GRPO really need to have a mixed batch of success and failure to get meaningful signal. Even SFT, which is generally more reliable, it has some risks as we've applied it to kind of mode collapse or loss of other behaviors in the model. I think we don't yet really understand the scope of what can be done with post-training, how we preserve steerability in our foundation models so we can do interesting post-training. There's a lot of opportunity for research there. But what I guess is fun is there's also a lot of opportunity for engineering and trying stuff. And we're seeing a lot of groups around the world trying stuff and writing blogs and tweets and hopefully occasionally a paper, about what they learned in that process.
So you guys talk about reasoning, and some of the questions that I see from the audience is, what is reasoning? So is it reasoning a kind of something that we can solve by pattern match, or is it something beyond the pattern match?
But we call it reasoning. I think your talk was good in some sense. That's not the right word. It's generating spurious tokens that the model can use to get to an answer. And that these additional tokens allow us to move in the space of this conditional, so that the final set of tokens are the right set of tokens. We as humans attribute that to reasoning. And in some sense, in the demonstrations we've given the model, we've tried to bootstrap that with what is human reasoning. But there isn't a constraint, certainly as we move in the reinforcement learning direction, that this coincide with the standard processes of human reasoning, at least unless we reward it to do so.
Wow.
Yeah, so I think first of all, I mean, you obviously know the answer, June, that there are ways in which we have formalized reasoning. For example, logical reasoning has been formalized, and certain kinds of logical reasoning can actually be connected to pattern matching. It's not one or the other. So, for example, databases are doing reasoning, but they're doing direct pattern matching. Detective databases go one level further. Total knowledge entailment winds up having logical reasoning thing. The other issue is, if I give you the correct answer to what you considered a problem that requires reasoning, that doesn't necessarily mean that I did reasoning the way you expected me to do it. I give this example of this Microsoft interview question where they used to ask people, why are manhole covers round? If you never heard this, the first time you heard this, you'd have to think and actually come up with a good answer. But right now, all you know is people have prepared for the interviews, because every damn interview question bank has this. And LLMs have basically not only seen every procedural question bank, during post-training, they're also seeing longer instances of how to solve different kinds of problems. And so in some sense, we are converting reasoning into a memory effect. And that is where we are right now. Nobody has shown otherwise. It's not simple pattern matching, but it's in the spectrum of pure retrieval and something like logical reasoning, we are still somewhere closer towards the retrieval side. But you're increasing the amount of data over which you get to do this retrieval.
So agentic AI requires planning, and the planning has unbounded length, as you say, right? And you're saying that there is actually no guarantee of success. Isn't that a worrisome issue?
Yeah, it gives me up. It gives me up.
What should we do?
It depends. It depends on the kind of world. If your world is ergodic, and many things where, until the credit card transactions get connected, calling the right source and doing the right tool calls, etc., it's still very painful amount of activity we do that LLMs are actually good at helping improve. So if you're sort of kind of in the loop, this is still very useful. If the overall thing is basically, by the way, I've seen agentic benchmarks, not the one that Joey may have done, but I've seen agentic benchmarks. Like for example, TowBench, you're looking to see whether they have examples with action interactions. No, they don't. They make sure that there are no action interactions. So if you actually make your domain ergodic, then it becomes easier. And by the way, when you have a small kid in your home, you make your living room ergodic. You make sure that there are no guns lying around, there are no sharp objects lying around, so that even if the kid doesn't know how to do planning, they won't get into major problems. And that is basically where we are. There are a large number of domains where failure is either soft or doesn't actually exist. So you can blunder your way from one place to another place. And that's where, if you're trying to improve, do various operations on some text so that it has a different format, etc., it's not going to hopefully end the world. Whereas if on the other hand, these are actions that actually have physical consequences, or even in the case of databases, you overwrite particular files, etc., those would make it essentially non-ergodic domains, and you need to make sure that the correctness is true.
We looked at this a little bit in the context of safety. It's a very good point. In the system world, we can often wrap things in transactions to create kind of the illusion of ergodicity. And one of the nice things about doing that is it allows the model to explore to some terminal state and then realize, I regret having deleted the file system. I'd like to roll that back. And so there is some value in preserving ergodicity in our environment so that we can have models that make that assumption and can explore more effectively. But it's a good point. Models generally aren't good about reasoning about the long-term consequence of their actions.
And if you have, like, in some sense with the transactions, my sense, if I get it correctly, in some sense, if you have simulators, then a world which is non-ergodic, but in a simulator, it is ergodic because simulators can be restarted. We try to learn in flight simulators because we don't want to kill flights. But then eventually you do have to learn, try to fly the real flights, and that's when things become important. So but then writing the simulator is actually a very interesting, costly affair where flight simulators have to have the understanding of the physics of the world, etc., to make sure that they're giving as good an information as possible to the agent as to what it can get out of this. Normally, this whole controversy about whether LLMs are learning world models or not, even though they are getting predictive accuracy correct, is connected to this. So they can tell you exactly very good paths in Manhattan, but the Manhattan map they learned actually is completely wrong. They can give very good predictions about solar planetary system interactions, but the actual model they learned is wrong. And so they can't use that model as a simulator. That's basically, again, connected to, if you do have a simulator, then an ergodic, non-ergodic world with a simulator is an ergodic world to some extent.
Okay, so that's a handful of discussions, and I wish we could have more time, but our time is running up now. Okay, so let's thank both Joy and Rao for the insightful discussions. Okay, so thank you.